Hello everyone. Today I'm excited to present a paper titled A Survey on Neural-symbolic Learning Systems for you. Artificial intelligence has evolved significantly from the logical theories of the 1960s to today's advanced machine learning. AI has mainly focused on two areas: perception, represented by neural networks, and reasoning, represented by symbolic systems. The motivation of this paper is to emphasized the importance of the fully understanding of neural symbolic learning systems and bridge the existing gap between symbolic and neural systems and overcoming the limitations of models that only focus on perception by highlighting the advantages of symbolic systems for their ability to reason and work well with other systems. Neural networks and symbolic systems are taking different problem-solving approaches. As you can see in the table, they use different processing methods, they use different knowledge representation and primary algorithms. Each of them has their own advantages and disadvantages. For example, the symbolic systems are has a strong generalization ability. However, they are weak at handling unstructured data. They has good interpretability, but they has a weak robustness. On the other hand, neural networks are strong at handling unstructured data. They has a strong robustness, and they are fast in learning. However, they have their lack of interpretability, and they are weak in generalizability. Uh, the challenge is how we can use these two systems simultaneously to have the advantages, to use the advantages in each systems to have a more accurate and interpretable uh, model that interpretable model. In in the following of this paper, the authors propose a novel taxonomy of the neurosymbolic learning systems. They provide a comprehensive overview of neurosymbolic techniques and discuss the applications of neurosymbolic learning systems and propose some potential future research directions. So generally, neurosymbolic learning systems are hybrid models that leverage the strengths of both symbolic systems, which use a reasoning-based approach on structured data, and neural systems, which excel the learning-based approach on unstructured data. Symbolic systems process information through symbols and acquire solutions through search algorithms, while neural networks operate on vectors and learn mapping function through training. This paper classified the neurosymbolic learning systems into three main categories: learning for reasoning, reasoning for learning, and learning reason. Here we can see more detailed structure of each category. In learning for reasoning, the goal is to leverage symbolic systems for reasoning while incorporating the advantages of neural networks. This could be done in two aspects. The first is to use the neural network to reduce the search space of symbolic systems and accordingly to accelerate the computation. The second approach, the second aspect is to use neural networks to provide the abstraction or extraction of symbols from unstructured data for symbolic systems, since the symbolic systems are not good with the unstructured data. In the second category, which is reasoning for learning, the idea is to leverage neural network, leverage neural systems for machine learning tasks while incorporating symbolic knowledge into training process to enhance the performance and interpretability. For instance, symbolic knowledge such as knowledge graphs, can be represented as a regularization term in the loss function of a specific task and help to improve the training and learning process and can be led to better generalization and interpretability of neural networks. In the third category, learning reasoning, the interaction between neural networks and symbolic systems are bidirectional. The goal is to strike a balance between involvement of neural systems and symbolic systems in problem-solving process. So the output of the neural network becomes an input of the symbolic reasoning component and vice versa. As mentioned in the previous slide, the methods for learning for reasoning can be divided into two groups. One is to accelerating symbolic reasoning, and the other is providing an abstraction of unstructured data into symbols for symbolic systems. Here we can see some of the proposed methods by researchers. I provided the reference for them at the end to learn more in details. Methods for learning, reasoning for learning can be broadly divided into two categories. One is a regularization method, which uh, integrates symbolic knowledge into training process by adding regular terms to the objective function of the model. And the second is knowledge transfer models, which establish a connection between different domains such as visual space and semantic space, and transfer the symbolic knowledge from one domain to another to support the learning process. Here we can see the example for each category. For example, CAZSL provides a knowledge graph for an object detection task. And for knowledge transfer models, you can see these DGP, KGTN methods that uses two different uh, models and try to provide knowledge from another model to improve uh, the other model. Here you can see some of the methods for third category, which is learning reasoning. As mentioned earlier, in learning reasoning, the learning and reasoning part are not work in isolation, and they work closely interacted. In deep problog, which is a probabilistic programming language, that combines deep neural networks with probabilistic logic. It uses neural predicts as an inference between neural network and symbolic reasoning. It utilized the sentential decision diagram for symbolic reasoning and end-to-end training with gradient semantics. ABL is another method which combines abductive reasoning with induction, bridge, machine learning, and logical reasoning. Utilize PropLog as knowledge-based abductive reasoning to revise pseudo-labels and deductive labels for training. WS Nesil is another method which employs an encoder-decoder framework with an encoder and two decoders. It provides supervised information for reasoning using back search algorithm and sampling technology. It uses a regular term of logic rules for reasoning and train iteratively until convergence. BBGR is another method which combines visual reasoning models and symbolic reasoning models and use MLN to model all logic rules for quantifying trigger symbolic knowledge and end-to-end training with variational EM algorithm. Further, the paper talks about the applications of this neurosymbolic system, which is object-visual relationship detection, knowledge graph reasoning, classification, and few-shot classification, intelligent question answering, reinforcement learning are some of the applications that use the neurosymbolic systems. Furthermore, the paper talks about the future research direction in neurosymbolic systems. First is efficient methods, which can be summarized in overcoming the challenges of interactable and precise inference and symbolic reasoning by exploring potential of neural networks to handle computationally difficult tasks. The other one would be automatic construction of symbolic knowledge, which address the time-consuming process of manually constructing logic rules by focusing on the automatic learning of logic rules from data, enabling end-to-end learning from rules derived from prior knowledge. The other one is symbolic representation learning, which is developing more robust and efficient symbolic representation learning methods, especially in capturing semantic similarities among predicates with similar semantic but different logical formulas. and exploring heterogeneous graph representation learning methods to handle diverse symbolic knowledge. And the last would be application field expansion, which is generally talks about using the neurosymbolic learning systems on the beyond existing domains and use it to new areas such as COVID-19 pandemic and advanced robotics, scaling methods, or the emerging new domains. As conclusion, the paper introduced a novel taxonomy for neural symbolic learning systems. It described the techniques employed in each categories to provide in-depth understanding for each neurosymbolic learning methods and explore a diverse range of application of neurosymbolic learning systems, and they're showcasing their versatility in various domains and discuss future research directions, emphasizing the need for semantic comprehensive exploration in the new fields. Here are some of the mentioned methods in this slide, and thank you for your attention.